look at a clock. Any clock. The one on your wall, the one on your phone, the small ticking circle on your wrist. Watch the seconds fall away, one after the other, each one identical, each one reliable, each one marching forward in that perfect, unwavering rhythm. Tick, tick. It feels absolute, doesn't it? It feels like the most trustworthy thing in the universe, this steady, universal drumbeat against which all of existence moves. Your morning coffee, the orbit of the moon, the slow burn of a distant star, all of it synchronized to the same cosmic metronome. Now, what if I told you that clock is lying to you? Not because it's broken, not because it's cheap, but because time itself, the very thing that clock is supposed to measure, is not what you think it is. It is not universal. It is not constant. It does not flow at the same rate for everyone, everywhere, in every circumstance. The seconds falling from your clock right now are not the same seconds falling from a clock on the International Space Station, or a clock aboard a jet racing across the Atlantic, or a clock sitting at the edge of a black hole. And the difference is not a matter of engineering or error. It is a matter of physics. It is a matter of reality itself. This is the legacy of one man's almost reckless act of imagination. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that would quietly detonate beneath the foundations of everything humanity thought it knew about the universe. His name, of course, was Albert Einstein, and the idea he introduced, the special theory of relativity, did not merely adjust our understanding of time and space. It dismantled it. It revealed that the universe operates according to rules so deeply counterintuitive, so profoundly strange, that more than a century later they still have the power to stop you in your tracks if you truly let them sink in. This is the story of that idea, and by the end of it, you will never look at a ticking clock the same way again. To understand what Einstein discovered, we need to start where he started, with two deceptively simple statements. Two postulates. They sound almost innocent when you first hear them, like rules for a children's game. But together, they unleash a cascade of consequences that reshapes the geometry of reality. The first postulate is this. The laws of physics are the same for all observers moving at a constant velocity relative to one another. This is called the principle of relativity, and in some sense, it's the less radical of the two. It means that if you are sitting in a perfectly smooth train moving at a constant speed, with the blinds drawn, there is no experiment you could perform inside that train to determine whether you are moving or standing still. You could pour a glass of water, toss a ball in the air, bounce light between mirrors. Everything would behave exactly as it does when you're sitting in your living room. Motion, in and of itself, is not something you can feel. It is not absolute. It is always relative to something else. This idea wasn't even new with Einstein. Galileo had articulated a version of it centuries earlier. If you've ever sat in a parked car and felt, for a disorienting moment, that you were the one drifting backward when the car next to you pulled forward, you've experienced this principle firsthand. There is no cosmic scoreboard telling you who is really moving. There is only motion relative to other things. The second postulate, however, is where the universe starts to misbehave. Einstein declared that the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. Let that settle for a moment because it is genuinely bizarre. In every other domain of human experience, speeds add up. If you're standing on a flatbed truck moving at 60 kilometers an hour and you throw a baseball forward at 40 kilometers an hour, someone standing on the roadside will measure that ball traveling at 100 kilometers an hour. That's just common sense. That's how velocities work, or so we thought. But light refuses to play by these rules. If you're on that same truck and you switch on a flashlight, the light leaving that flashlight does not travel at the speed of light plus the speed of the truck. It travels at exactly the speed of light, not a fraction faster. And the person on the roadside? They also measure that light at exactly the speed of light, not a fraction slower. The number is always the same. Approximately 299,792,795,458 meters per second. Always. For everyone. No matter what. Now, this should strike you as almost offensively unreasonable. How can two people, one moving and one stationary, both measure the same beam of light at the same speed? If one of them is chasing the light, shouldn't they see it moving away more slowly? If one of them is racing toward it, Shouldn't they see it approaching faster? Every fiber of intuition screams yes. And every fiber of intuition screams yes. And every fiber of intuition is wrong. Before Einstein came along, physicists had actually already stumbled into this mystery, though they didn't fully grasp what they had found. In 1887, two American scientists, Albert Michelson and Edward Morley, conducted one of the most famous failed experiments in the history of science. At that time, physicists believed that light, like sound, needed a medium to travel through. Sound moves through air. Waves move through water. So light, they reasoned, must move through some invisible, all-pervasive substance they called the luminiferous ether, a kind of cosmic fabric that filled all of space. If this ether existed, then the Earth, as it orbited the sun, would be plowing through it like a boat through still water. And just as a boat creates a current around itself, the Earth's motion through the ether should create a detectable, a ether wind. Light traveling in the direction of Earth's motion should be slightly slowed, like a swimmer pushing against a current, while light traveling perpendicular to Earth's motion should be unaffected. Michelson and Morley built an extraordinarily precise instrument, an interferometer capable of detecting even the slightest difference in the speed of light traveling in two perpendicular directions. They found nothing, no difference, no ether wind. No matter how they oriented their apparatus, no matter what time of year they performed the experiment, the speed of light was stubbornly, maddeningly identical in every direction. The scientific community was baffled. Some physicists proposed elaborate explanations. Maybe the Earth dragged the ether along with it. Maybe the apparatus was contracting in just the right way to hide the effect. But these were patches, bandages over a wound that would not close. It took Einstein to see the result for what it truly was, not a failure, but a revelation. The speed of light isn't constant because of some quirk of the ether or some accident of measurement. It is constant because the universe is built that way. It is a fundamental feature of reality, woven into the very structure of space and time. And once you accept that, truly accept it, not as a curiosity but as a law, everything else begins to unravel and reassemble in astonishing ways. The first thing that unravels is time. To see how, let's conduct a thought experiment, one that physicists have used for over a century to make the strangeness of relativity vivid and undeniable. Imagine a clock, not an ordinary clock with gears and springs, but something far simpler and more elegant, a light clock. Picture two mirrors, one at the top and one at the bottom, separated by a fixed distance. A single pulse of light bounces back and forth between these mirrors. Each time the pulse completes one round trip, bottom to bottom, the clock ticks. It's the purest timekeeper imaginable, because its rhythm depends on only two things, the distance between the mirrors and the speed of light, both of which are constants. Tick, tick, tick. Now, place this light clock aboard a spaceship. The spaceship is sitting still relative to you, and you watch the light pulse bounce straight up and straight down. The path of the light is a simple vertical line. The clock ticks at a rate that seems perfectly normal. No surprises so far. But now, the spaceship begins to move. It glides past you at a significant fraction of the speed of light, say, 80%. From the perspective of the passengers on board, nothing has changed. They are floating in their cabin, weightless and comfortable, watching their light clock tick away at the same steady rhythm as before. The pulse goes straight up, bounces off the top mirror, comes straight back down. Tick, tick, tick. Remember the first postulate. The laws of physics are the same for all observers in constant motion. The passengers have every right to consider themselves stationary. Their clock works perfectly. But now, look at what you see, standing outside, watching the spaceship streak past. From your vantage point, the spaceship is moving sideways while the light pulse is bouncing up and down. This means the light, in your frame of reference, isn't traveling a simple vertical path anymore. It's tracing a diagonal, a zigzag, because the bottom mirror has moved sideways by the time the light reaches the top mirror, and the top mirror has moved again by the time the light returns. The light is covering a longer path. Think of it like rain falling straight down on a still day. If you start running, the rain seems to come at you at an angle, and if you trace the path of a single raindrop relative to you, it would be a longer diagonal line rather than a short vertical one. Here is where the second postulate delivers its stunning verdict. The speed of light is the same for you as it is for the passengers. The light on their ship is not moving faster just because the ship is moving. It is covering a longer diagonal path at the exact same speed. And if it's covering a longer distance at the same speed, then it takes more time to complete one tick. Their clock, as seen by you, is ticking more slowly. Not because anything is wrong with it, not because some force is acting on it, but because the geometry of the light's path through space, from your perspective, has stretched. This is time dilation. And here's the part that truly knots the mind. It is not an illusion. It is not an artifact of observation. The passenger's clock is genuinely, physically, measurably ticking more slowly relative to your clock. If the passengers had a twin sibling who stayed behind on Earth, and the spaceship flew out to a distant star and returned, the traveling twin would have aged less than the twin who stayed home, not metaphorically, not subjectively. Physically, the cells in their body would have divided fewer times. The thoughts in their mind would have been fewer. They would be younger, in every concrete biological sense, than the sibling they left behind. At the speeds we encounter in daily life, driving a car, riding an airplane, even launching a rocket, the effect is vanishingly small. A passenger on a commercial jet flying for an entire year would have aged perhaps a few microseconds less than someone who stayed on the ground. It's real, but it's imperceptible. However, as you approach the speed of light, the effect doesn't just grow, it explodes. At 90% of the speed of light, time on the moving ship passes at roughly 44% the rate of time on the ground. At 99%, it drops to about 14%. At 99.99%, time practically freezes. A year on that ship might correspond to centuries, millennia, or even longer back home, depending on just how close to the speed of light you travel. And at the speed of light itself, if you could somehow reach it, which no massive object can, time would stop entirely. A photon, a particle of light, does not experience time at all. From the moment it is emitted to the moment it is absorbed, whether that journey spans the width of a room or the width of the observable universe, a photon's experience of elapsed time is zero. It exists in an eternal, frozen now. But relativity has another shock in store, one that goes even deeper than the stretching of seconds. It attacks something we rarely think to question, the idea that events can be simultaneous. Imagine you're standing exactly in the middle of a long train platform. At the precise moment you're standing there, two bolts of lightning strike, one at the far left end of the platform and one at the far right end. Because you're equidistant from both strikes, the light from both flashes reaches your eyes at exactly the same instant. You conclude, quite reasonably, that the two strikes happen simultaneously. Now, imagine a passenger on a train racing through the station from left to right at high speed. At the moment the lightning strikes, this passenger also happens to be right next to you, in the middle of the platform, in the middle of the train. But here's the crucial difference. The passenger is moving toward the right-hand flash and away from the left-hand flash. The light from the right-hand strike has a shorter distance to travel to reach the passenger's eyes, while the light from the left-hand strike has a longer distance. And because light travels at the same speed in all directions, that stubborn, magnificent constant, the right-hand flash reaches the passenger first. The passenger sees the right-hand lightning bolt hit before the left-hand one. And this is not a mistake. This is not a delay caused by signal processing or slow reflexes. From the passenger's equally valid frame of reference, the right-hand bolt genuinely happened before the left-hand bolt. They were not simultaneous. Two events, two observers, two completely different orderings of the same reality. Neither of them is wrong, neither of them is being tricked. They simply inhabit different frames of reference, and in those frames, the timing of events is different. The implications of this are staggering. If simultaneity is relative, if the order in which things happen can depend on who is watching, then our everyday notion of a universal now crumbles to dust. Your present moment is not the same as the present moment of someone flying past you at high speed. There is no single definitive snapshot of the universe at any given instant that all observers would agree upon. The past, the present, and the future are not rigid, universal categories carved into the fabric of reality. They are, to some extent, a matter of perspective. Now you might be wondering, is this all just theoretical elegance? Mathematical poetry with no connection to the real world? Far from it. Time dilation is not just predicted by the equations, it is confirmed over and over with extraordinary precision in experiments and technologies that shape your daily life. Consider the Global Positioning System, GPS. The satellites that make GPS work orbit the Earth at an altitude of about 20,200 kilometers, moving at roughly 14,000 kilometers per hour. At that speed, special relativity predicts that their onboard clocks should tick slightly slower than clocks on the ground by about 7 microseconds per day. That doesn't sound like much, but GPS works by timing signals to nanosecond precision. If the relativistic time dilation were not accounted for, and there is also a general relativistic effect from gravity that we'll touch on shortly, the system's position calculations would drift by roughly 10 kilometers per day. Your phone would tell you you're in the middle of a lake when you're actually in a parking lot. Every GPS satellite carries corrections for relativistic time dilation built into its firmware. Every time you use a map on your phone to navigate to a restaurant, you are relying on Einstein's theory of relativity. The 20th century's most abstract physics is quietly running the 21st century's most mundane technology. But there's an even more direct and dramatic confirmation of time dilation, and it comes not from satellites but from subatomic particles called muons. Muons are created high in Earth's atmosphere when cosmic rays, high-energy particles from deep space, slam into molecules of nitrogen and oxygen about 15 kilometers above the surface. Muons are unstable. They decay rapidly with a half-life of about 1.5 microseconds. Even traveling at nearly the speed of light, a muon should only be able to cover about 450 meters before it disintegrates. By all rights, muons created 15 kilometers up should never reach the ground. They should vanish long before they get here. And yet, they arrive in droves. Physicists detect enormous numbers of muons at the Earth's surface, far more than should survive the journey. The explanation is time dilation. Because the muons are traveling at roughly 99.9% of the speed of light, time in their reference frame passes much more slowly relative to our clocks on the ground. From our perspective, their internal clocks are running slow, stretching their brief 1.5 microsecond lifespan into something much longer, long enough to traverse the full 15 kilometers and slam into our detectors. And from the muon's perspective, something equally fascinating happens. The muon sees itself living for the normal 1.5 microseconds. But from the muon's frame of reference, the distance between the upper atmosphere and the ground is dramatically contracted, another consequence of special relativity called length contraction. The Earth's atmosphere appears much thinner, so the muon has no trouble crossing it in its short life. Two perspectives, each internally consistent, both agreeing on the observable outcome. The muon reaches the ground. This is not an abstraction. It is a physical phenomenon you can measure with a particle detector and a stopwatch. The universe is doing this constantly, right above your head. All of these revelations, time dilation, length contraction, the relativity of simultaneity, might seem like a collection of strange, disconnected curiosities, but they're not. They are facets of a single unified geometric truth about the universe, and it was not Einstein himself but his former mathematics professor, Hermann Minkowski, who saw this most clearly. In 1908, Minkowski stood before an audience of scientists and declared, with the confidence of someone who has glimpsed something both beautiful and irreversible, henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. What Minkowski realized was that space and time are not separate stages on which the drama of physics unfolds. They are a single entity, space-time, a four-dimensional fabric in which 3 dimensions of space and 1 dimension of time are interwoven so tightly that you cannot affect one without affecting the other. Think of it this way. Right now, as you sit and listen to this, you might feel perfectly still. But you are not still in space-time. You are always moving through space-time, at every moment without exception. If you are sitting motionless in space, not walking, not driving, not orbiting, then all of your motion through space-time is directed entirely through time. You are barreling through time at the maximum possible rate. Your clock ticks as fast as it can tick. Your seconds are as full and fat as seconds can be. But the moment you begin to move through space, the moment you stand up and walk, or board a plane, or climb aboard a hypothetical spaceship, Some of your motion through space-time gets redirected. A portion of your movement that was aimed purely through time is now aimed partly through space. And because the total rate of your motion through space-time is fixed, always equal to the speed of light, for every object at every moment, the more of that motion you divert into space, the less you have left over for time. Your clock slows down. Your seconds thin out. This is perhaps the most beautiful and haunting insight of special relativity. There is a cosmic speed budget, and it is always exactly the speed of light. You are always, at every instant, traveling through the combination of space and time at this one fixed rate. If you devote all of it to time, you sit still in space and age as fast as possible. If you devote all of it to space, if you somehow travel at the speed of light, you have nothing left for time. Time stops. This is not a metaphor. It is not poetry dressed up as physics. It is the literal mathematical structure of the universe. The trade-off between space and time is governed by a geometry, Minkowski geometry, that is as rigorous and precise as the Euclidean geometry you learned in school, just profoundly stranger in its implications. And light? Light is the boundary. Light is the thing that moves entirely through space and not at all through time. It is the entity that maxes out the spatial component of the speed budget, leaving exactly zero for the temporal component. This is why nothing with mass can reach the speed of light. To do so, you would need to have zero passage of time, and for a massive object, that would require infinite energy. Light doesn't have this problem because photons are massless. They were born on the boundary, and they will stay on the boundary, existing in a state that we, as beings trapped in the flow of time, can barely fathom. This geometric picture also illuminates why the speed of light appears constant to all observers. It's not because light is doing something strange. It's because space-time is structured in such a way that every observer, regardless of their motion, measures their own passage through time and their own distances through space in a way that always yields the same speed for light. The constancy of the speed of light is not a quirk. It is a structural feature of space-time, as fundamental and non-negotiable as the fact that the angles of a triangle on a flat surface add up to 180 degrees. You don't ask why the angles add up that way. It's simply what it means for the surface to be flat. Similarly, you don't ask why the speed of light is constant. It's simply what it means for space-time to be Minkowski space-time. Step back now and consider where we've arrived. We began with a simple ticking clock and a conviction, shared by virtually every human being who has ever lived, that time is universal, absolute, and indifferent to the circumstances of the observer. And we've discovered that this conviction is profoundly, spectacularly wrong. Time bends. Time stretches. Time depends on how fast you move. The present moment is not shared. The past and the future are not the same for everyone. The tidy separation between space, the stage in which things happen, and time, the invisible river that carries us forward, is an illusion born of living at slow speeds in a small corner of the cosmos. Strip away that illusion, and what you find is something far more magnificent, a four-dimensional tapestry in which every movement through space is a negotiation with time. Every tick of every clock is a local phenomenon shaped by its own history of motion, and the one unchanging thread holding it all together is light. The cosmic constant, the ultimate speed, the boundary between time and timelessness. And what is perhaps most astonishing is that this is not the end of the story. Everything we've discussed today falls under the umbrella of special relativity, the physics of objects moving at constant velocities in the absence of gravity. 10 years after his 1905 paper, Einstein went further. He published the general theory of relativity, which revealed that gravity itself is a warping of space-time, that massive objects like stars and planets bend the fabric of the universe around them, and that this curvature also affects the passage of time. Clocks tick slower in stronger gravitational fields. Time at the surface of the Earth runs more slowly than time on a mountaintop. Time near a black hole nearly stops altogether. The rabbit hole goes deeper than we've gone today, and it only gets more breathtaking the further down you go. But for now, sit with what you've learned. Sit with the fact that the clock on your wall, that reassuring, rhythmic, seemingly objective clock, is telling you a story that is true only for you, only in your frame of reference, only given your particular motion through the cosmos. Someone else, somewhere else, moving differently, would hear a different story from the same clock, and both stories would be true. The universe is not what it appears to be from our slow, small, human-scale vantage point. Beneath the surface of every ordinary moment, every footstep, every heartbeat, every lazy afternoon watching the shadows move across the floor, there is a deeper reality, written in the language of light and geometry, in which time and space dance together in ways that are at once mathematically precise and almost unbearably beautiful. The next time you look at a clock, let yourself feel it. That tick is not universal. That tick is yours. It belongs to your path through space-time, your speed, your story. And somewhere out there, on a muon screaming through the atmosphere, on a satellite drifting above the clouds, on a photon that has been traveling since the first moments of the universe and has not experienced a single second of time, somewhere, the same moment is unfolding differently. That is the universe Einstein revealed. Strange, elegant, and far more wonderful than any clock could ever tell you.